welcome to Heap Exploitation, Pwn 4, right? Some crazy stuff now. It only gets harder from here. So first of all, some announcements. After spring break, we'll play Dice CTF. It's a really cool CTF. They had some cool heap challenge, or a cool heap challenge last year, because I spent all my time on that one, so I didn't actually see the other ones. But yeah, if you want to see some cool heap pwn, come to Dice CTF. And then here's a meeting flag. I'll give you like a minute or so to type that in. Yeah. And then here's is that an XKCD? I don't actually know, but like it's a funny image. Yeah. Yeah, it's a heap. Unfortunately, we'll not be dealing with that kind of heap today. So we're dealing with the worst kind. Okay, it'll also be at the end too. You can quite enter that, but actually, I should hide this thing. Okay, so here's the memory layout again as a refresher. So previously we've talked about things like the text section, which is where all the code is, like we talked about in ROP. Obviously, we've done stuff with the stack, buffer overflows and stuff, but we've never really talked about the heap yet. So that's what we're going to talk about today. So the reason why this even exists, I guess, is like with all the challenges are just like generally what we've seen before is fixed size buffers like static size buffers on the stack. And so there's two problems. First is like how do we I guess allocate something dynamically at runtime? Like the size of whatever we're trying to allocate is different with depending on how the program runs. And the other issue is how do we actually return an address to something we allocate in a function? So like, for example, in this like little snippet here, if we return this like a pointer to this buffer buff2 on the stack, first of all, you can't allocate based off the size here, but like say that was possible. If you return this buffer, it will actually like deallocate once the function is ended. So you can't actually return a buffer that's something someone else can use out of a function. And so this is where the heap comes in. It's not the data structure. It is.
It used to be. I think that's what it's called. Heap.
Really?
Yeah.
I see.
Right.
Well, it's not the data structure anymore. Now it's much, much worse. But so this allows dynamic memory allocation, and the allocations don't get deallocated after the function that allocated them like exits. So the two, I guess, core functions associated with the heap is malloc, which allocates data on the heap and returns a pointer to that data, and free, which frees that data, I guess, releases that data. So, and like small detail, like regardless of the size you put, there's a minimum size for a chunk on the heap based on alignment and like metadata. So it's 32 bytes with 24 bytes of usable memory. So then like an example, like using the heap, you'll see call to malloc, pass in the size that you want to allocate on the heap, and you'll get a pointer to that region of memory, which you can manipulate the same way that you would do normally. And then at the end, you have to free that buffer, otherwise you'll get a memory leak, and 341 core staff will be really mad.
Oh, an interesting point is that there's a bug in this code. Who can say what the bug is? I don't know if it's exploitable necessarily. I think it actually even might be, but there is a bug here. I mean, you could, at minimum, you could make this crash.
Are you passing a really lower size?
Sure. Let's say they do like you edit this code and you say, okay, if size is greater than like 1,000, then we will just exit. There's still a bug in this code. size is 0, then you're still fine because I less than size is always false, right? So like there's no, I mean, the function will do nothing, but it won't crash.
Well, size can be negative.
Yeah, exactly. So they're type confused. So size malloc takes a what do you call it? Unsigned integer size. The function takes a signed integer. What happens if you pass -1? It will pass any like length check, right? Any bounds check will pass, but you will give malloc like some insane size. And I mean, it will either just crash or like return null or something, but like your program will probably crash.
Yeah, I mean, if malloc like freaks out, yeah. If it returns null, that's not that big of a deal. But
Yeah.
yeah. Okay. So here's like a, I guess, high level, like oversimplified model of the heap. So like usually what glibc malloc has is what's called a top chunk, which is just like this big sort of already requested, like memory that's already been requested from the OS that it just keeps. And then when a user requests a memory via malloc, it will break off a piece of that top chunk and give that to the to the whoever called malloc. So like if we allocated 2 chunks here, like we first allocated A, would break it off the top chunk and put it directly adjacent. And then if we allocate B, it will break it off the top chunk again. So actually B is I guess above A in memory. And then we can free A and when you allocate C, assuming C is the same size as A, instead of breaking off from the top chunk again, it can use the chunk that was freed before when A was free. So when you free a chunk, what happens at a high level is it gets added to some sort of free list. So for now, we'll just think there's one free list that basically is just a linked list of all the free chunks in the heap. And so when you malloc a chunk with like a similar size, maybe like slightly lower, or ideally exactly the same size as a chunk in the free list, then it will, instead of requesting memory from the OS or like you taking from the top chunk, it will instead use that chunk that's in the free list. And so this is so that you don't end up using too much memory, like wasting a bunch of memory. And so in later you'll hear us talk about something called bins. Each bin is basically just either doubly or singly linked list. And yeah, and in order to like maintain this list, extra metadata, like as in like forward and back pointers for the list, get added to the chunk to yeah, maintain the free list. So like this is what that metadata sort of looks like for in-use and a free chunk. So an in-use chunk will have, well, the core metadata is just the size, and then so the arena and whether it's M-mapped or not are not something you really need to worry about here. The preven use flag is pretty important. It says whether the like previous chunk adjacent in memory is in use, and that is important for coalescing and is also pretty important for some exploits. But and then for a free chunk, in order to sort of like conserve memory, it actually uses the like a portion of the user data to store to store some of the metadata associated with the free list. So that way, it doesn't actually need to have unused metadata for in-use chunk for the free list. It can instead just use some of the user data for that. And that's also why there's like a minimum size for a chunk. But that should, your security like alarm bell should be going off, right? Like, oh, there's pointers that are now in the same area as user data. So like, there could be some crazy things that happen because of that. But yeah, also, another thing that like, I guess causes a lot of fancy exploits to happen. I mean, not on its own, but like it allows some cool things to happen is coalescing and splitting, mainly coalescing. But so coalescing is when you have 2 free chunks that are adjacent in memory. You combine them to form one larger free chunk. And the reason why you do that is so that if someone requests like maybe like a larger region or a larger piece of memory, you can still use those free chunks instead of like taking from the OS or from top chunk and using more memory. And so splitting is like kind of solves the same issue, or like there's two types of like fragmentation. Splitting solves a different type of fragmentation where you have unused memory within a chunk. So we can split that chunk to create another free piece of memory that can potentially be used later. Yeah, so these are two kind of important parts of the way malloc works. Yeah, and so now we'll start getting into the details. You don't actually need to know the stuff I'm about to go into right now for like most of the challenges, except for the last one, but or maybe the last two, but like these are also pretty important for solving heap challenges. So the way malloc doesn't actually have one single free list. Instead, it will have multiple free lists called bins, which it will sort of categorize by size in order to make it so that like free chunks are efficiently looked up and returned rather than having to search an entire free list. So the first one is called T-cache bins, which is actually a relatively new addition compared to the other ones at least. So there are 64 of these, each associated with a size, and they're also thread specific. Each thread has them, so or has its own T-cache bins. So like there's a max of 7 free chunks that can be in a T-cache bin at a time, and so yeah, this is basically an optimization because in multi-threaded context, because you don't have to lock the heap or the arena. A thread doesn't have to do that if it's using a T-cache bin. But yeah, so because these are meant to be pretty fast, they have some like a lot lacking security checks, and yeah, they're also singly linked, and yeah, they have a fixed size. So, and fastins are like pretty similar. It's like basically the overflow of T caches hit their like size limit, then they start going into fast bins. They are not coalesced, which is another optimization. And again, these also so they're not like coalesced immediately, but like malloc will occasionally coalesce free chunks when it needs to allocate a large piece of memory, for example. But yeah, these are singly linked, and they are and they also skip some security checks, which is important for some of the challenges. Unsorted bin is another optimization that when a chunk is freed, we don't immediately want to like coalesce it if the same size chunk is just going to be allocated again. So instead, we first put it in an unsorted bin and wait to see if that chunk will immediately be reused again. If not, then it will sort it into a smaller large bin, which are unsorted small and large bins are the ones you probably don't need to understand as well. In challenges, you'll see more common. In challenges, you'll see T-cache bins and fast bins a lot more commonly. But yeah, small bins are also fixed size bins in that each linked list corresponds to a fixed size chunk. There's 61 bins, and the difference between this and fast bins is one, it's doubly linked, and two, adjacent chunks will be coalesced and then like move to different bins. And finally, large bins store a range instead of like each linked list stores a range of sizes instead of a fixed size. And also the linked list is sorted, and yeah, it's also circular doubly linked. Yeah. So this is now what kind of our like still basic model of the heap looks like. There's like you can see these 5 bins, the T-cache and fast bins and small bins all have specific fixed sizes, and then large bins have ranges of sizes that correspond to these chunks or hold these chunks. And yeah, so then we'll talk about some I guess like other functions associated with malloc. One is the first is calloc, which allocates, like I don't know why it has like a different syntax, but like allocates items times size bytes instead of just passing a number of bytes. And it also
if items times size overflows.
I see. Yeah, but yeah, and it also mem sets this to 0. So Oh, and yeah, it does not use the T-cache, but realloc, that's a function. If you see that in opponent challenge, you should run as far as possible because this function is a mess, can't understand what's going on. And yeah, it will sometimes free things, sometimes malloc things, sometimes split things, sometimes coalesce things. And yeah, but basically it given a malloc chunk, it reallocates the size to whatever you want, whatever you pass it. And yeah, malloc sucks to understand. There's many optimizations, there's many security features that are added and removed, and so reading source is helpful, but also like it's hard and it changes a lot. So a lot of times the best way to understand how like how something is working in a challenge or just like how a malloc implementation is working in general is just to experiment, to play with it. You can do that in the challenges a lot without the need for GDB or Pwn tools by just like running the commands and seeing how the chunks are allocated. But yeah, so now we'll go on to the actual exploitation.
Okay, so show of hands, how many people are confused right now by malloc? Good, because everybody's hand should be up. It is very confusing, very complicated, and that is kind of why it's exploitable. Because like if you have something simple, it's easy to secure it, right? Like if you have a 10-line piece of code, it's probably easier to make it secure. Malloc is extremely complicated. There's like pointers everywhere. And there's defenses, but then they're all always imperfect because of how complicated it is. So we will kind of get into, do we have a clicker?
No.
So yeah, we'll get into kind of a little bit in the weeds of some of the exploits, but because it's kind of complicated, I wanted to show this diagram. This is from a paper from like a while ago, but this is like every Pwn challenge. Every Pwn challenge, like a CTF challenge, like a real world like zero-day exploit, broadly will follow this pattern. So it usually starts with violating memory safety. So you will get somehow an invalid pointer. Either you like go out of bounds, or you get like a dangling pointer, which is something we will see with malloc. And then you use this invalid pointer to either read or write. If you use it to write, you can corrupt data. You can corrupt, if you only corrupt data and your exploit ends there, that's what you would call a data-only attack. I think the first few heap challenges are
Yeah.
data-only.
Yep.
So yes, the first few heap challenges, you will not be hijacking control flow, you will only be corrupting data in the program. So like an example of this, right? Like let's say the program stores your username, right? If your username is equal to root, the program will give you full access. Let's say you manage to corrupt some data and change your username to root. Like you don't need a control flow code execution at this point, like you're done. Or you can use your data corruption to basically hijack the program. This usually involves modifying, like there's modified code, but nobody really does that anymore because like code is usually non-writable these days. So the more common exploit is to modify a code pointer. So row 3 middle. You can either modify a code pointer to point to shellcode, which is just your injected code that will execute and usually open a shell. Again, like now there are defenses against this, like data execution prevention, like NX or whatever. So that's usually less common. Or what you do is you reuse code that's already in the program. So that's like if you came to the route meeting, that's basically what that is, or like a returning to libc kind of attack. And then you get a control flow hijack. I mean, there's also like an implicit step where the pointer, like the program shouldn't figure out that your pointer, like you manage to corrupt the pointer and crash the program or something. But this is what every Pwn challenge looks like. This is what every Pwny CTF Pwn challenge looks like. So if you are kind of stuck on a challenge and like you are kind of too lost in the details, this is kind of useful to look at. Like you can kind of get some high-level overview of what you really want to do. Because like even when you do a challenge, these are sort of the steps that you kind of think through. Like first you try to look for some memory error, like maybe you look for a stack overflow, or maybe in the case of heap, we'll look at some errors. And then you might choose to correct some data and whatever. So what do we, again, at a high level, what do we want to do when we exploit programs? One option is code execution. There are many ways to achieve this. One common way is that you corrupt the return address on the stack. So like your basic stack smashing buffer overflow attack does this, route does this. You can do this also with the heap. And kind of at a high level, there's like these two primitives. An arbitrary read basically says, given this address, I can read the data at this address. This is useful if you want to maybe leak, let's say, like a cryptographic key that's stored in the program. Maybe you want to leak some address in the program and break. Have they done ASLR yet? Should have.
Yes.
Yeah. So if ASLR is enabled, like address randomization, an arbitrary read is what would let you break it. An arbitrary write is kind of more powerful. It says, given an address and a value, I can write this value to that address. Once you have that capability, like it's basically game over usually. And yes, if you can arbitrarily write to the stack, I mean, you know where the stack is and you're able to write to it, you can usually hijack the program, because you can do rob and back to libc and so on. Questions? Yeah.
Okay, this is like tangential that
Sure.
I want to ask you. What's the difference between a common kernel allocator versus a libc allocator?
Sure. So a memory allocator is written to, I mean, one of the main goals is to optimize performance, right? And the performance has to be optimized to the kinds of use cases that the allocator is going to be used in. So a user space allocator like malloc, glibc malloc, is going to be used in a very wide range of things, right? Like everything from a database to like a web server, games, like all kinds of things are going to use malloc. So it has to be kind of as general as it possibly can. The kernel's allocator, I mean, the kernel developers know what the kernel's code looks like, right? And it's fairly stable. So they know what the memory allocation requirements of the kernel are. So they can optimize an allocator to their requirements. So I think the kernel's allocator is a slab allocator.
Yep.
So it, like one of the things like optimizations it does is it keeps a pool of initialized objects of different kinds ready at all times. Like if you, let's say, open a file, right? The kernel probably has to allocate some file structure object, and that object always looks the same. So there's no need to like go in and, you know, allocate a chunk of memory, initialize it. It just keeps it ready. So it's mainly just, it's a different use case. So it's like different optimizations involved. Yeah, I mean, you have, what's it called? You have the kind of allocator that will, the free will not do anything. So you just allocate a whole bunch of memory and then you clear it all at the end. Like that's another allocation strategy. Like, let's say, I mean, the canonical example is a video game. If you are playing like level 0 and there's like 5 sprites on the screen and maybe a few objects, the thing will allocate a bunch of things. It will never free anything. Even if you kill the enemy, it's not going to free their sprite. But let's say you finish the level, then it's going to free everything. It's much easier to just free a whole block, right? Because freeing doesn't mean you like clear the memory. Freeing just means you change like your right. Okay, so we want to achieve these primitives by using malloc. I guess question for the audience: you've seen kind of what overall a overall a PWN exploit looks like. You've seen what malloc looks like. What do you think are some of the exploitable like features of malloc? What kinds of things in the malloc implementation do you think are like a little problematic? Because there's a lot of problematic things in the malloc implementation, and like even without kind of knowing all the details, I think you should be able to get some intuition for like what would you target. Like let's say I gave you the like magic ability to write like any metadata of any chunk, right? What might you decide to write? Ideas? It's fine if it's a wrong answer. Like it's useful to like the reason I want to have you think about this is that like once you get into the weeds with malloc, it's like extremely confusing. It's like everything is so complicated and it's like it's very easy to kind of lose the big picture. So what kind of are you really, I mean, what data inside?
And
Yeah,
I'll bring
so-
up the metadata.
Right,
to
so
see.
like here's what's stored in an in-use chunk and a free chunk. Like which of these things do you think are worth corrupting? Like, sorry, size, yes, size is good because I mean if you corrupt like the state of the allocator, that's potentially powerful. There's something that's even more direct. Like size will get you there. Like there's exploits involving corrupting size. There's something very obvious here that so I'll give you a hint. It's on the right side. It's not on the left. Because on the left, the payload is just user data, right? So that maybe it's worth corrupting that in some cases, but there's something very obvious on the right side that is extremely vulnerable.
You have the 409.
Yeah, exactly, right? You have two pointers here, and malloc is going to use these pointers in like unboundedly complicated ways. If you corrupt these pointers, then like anything could happen, basically. Yes.
So just a side note, which of these flags indicates whether it's being used chunk or free chunk?
Yeah, so actually the way malloc does it is a little different. It does not a chunk does not have any metadata saying whether it's free or not free, because it actually stores whether the previous chunk in memory is free or not free.
Yeah.
The reason why is because the reason when the times that it checks whether a chunk is free or not is when it's trying to coalesce, because if it will combine two free chunks, but it has to know that the like previous or next chunk in memory is free. The next chunk it could find just by adding the size of the current chunk, right? But the previous chunk, it can actually use this prev size field to jump back and then check there. But instead, what malloc likes to do is actually have a bit just for whether the previous chunk is in use. There's actually another subtle reason why that this is more important, which is that actually prev size is also user data. So you can't necessarily trust that you jump back, that you can jump back and check. And yeah, there's some fancy things with that. But yeah, that's how it works.
So in this context, previous and next are immediately previous next in terms of.
No,
No.
yeah, okay, so yeah, that's a very good point. I guess one thing that confused me when I learned this, is that all of this stuff is completely like imaginary. Ultimately, it's all just memory, right? It's all memory. All of this is stuff that malloc is putting on top of this memory. Like all of these linked lists, they do not actually exist. There are all of these pointers that give you these linked lists, but there is no like your RAM stick has no chunks in it. It's just memory. So one way of looking at the memory is just sequential in order of memory addresses, and that gives you a sequence of chunks. And that's kind of what the prev use flag is referring to. So it's literally the previous chunk in memory. The other thing is all of these linked lists, which malloc stores internally and are completely made up. And that's what the forward and back pointers are for. So if you have a free chunk, like malloc puts the free chunks into a linked list, again, completely conceptually, right? The next chunk may be somewhere completely different. You just have a pointer to that chunk for there. So the forward and back are pointers to the linked list chunks. And that only matters for free chunks. Like malloc will not link allocator chunks.
Again, a side note, do they check for use of the freeze? If so, how do they check?
Check for use, yeah, okay. So there are some, I guess that's also a good point. It depends on libc version. Like there are defenses in some libc versions that aren't there in others. Use after free specifically, I don't think there's.
I don't
really
think there's any protection.
Yeah, because like how
We will talk about something later to protect or like sort of protect these pointers.
right.
But actually detecting a use after free is something that I'm not.
Because like there's always like a trade-off between performance and security, right? Like if I like I could implement a very nice solution that just keeps track of every allocated and free chunk. I trap on every memory read and write, and I check is this chunk free or not, or allocated or not. Like it would work. I mean, my program would be like 100 times slower, and nobody wants that. Like generally, people are usually like you will see this everywhere, right? People are ready to accept bad security if it gives them performance. And that is, yeah, chip design, passwords, like everything. It's the same kind of principle. Okay, so actual attacks. Well, as you know, we will skip the slide.
The chunk is not aware of its next chunk's point, right?
What do you mean next chunk's pointer?
Because it has the previous chunk pointer.
It has a previous pointer. Oh, you
sorry.
mean like the next chunk's like state? Like is it
No,
free or
it's
not?
the pointer to the next chunk.
Wait, what do you mean by previous chunk pointer?
Next as in next in memory or
Yeah.
next in the free
I think
list?
the question is, does the currently used chunk have a forward or back?
No.
For a free list? No, because it's not in a free list. So like there's two, I guess, interpretations of next and previous,
Yeah.
right? There's like you could talk about next as a next chunk in the free list versus previous chunk in the free list because it's a linked list, right? Or you can talk about like next and previous as like literally two chunks adjacent in memory. So the next chunk is, so when I say like, when I talk about coalescing with next and previous chunks, what I'm talking about is next and previous chunks in memory. So actually the chunk doesn't store any pointers to those.
What's your contiguous?
It's contiguous, so it can use its size, or it also has a prev size field or a boundary tag, if you've heard of
There
that.
aren't actually. But it's kind of like
Well, it's like based on how they like it's pretty much a boundary tag.
Sure.
So like, yeah, so that's the way that it gets the next and previous chunks. So yeah.
Yeah, because like you can take the chunk and you can add the chunk size and you get to the next chunk. You can
Right.
subtract the previous size and you get to the previous chunk. Okay. Use after free. This is one of the memory errors associated with malloc. So what is the use after free? It's kind of self-explanatory. You have a allocated chunk, you free it, but then you continue for whatever reason to use it. Like ideally, once you free a chunk, the pointer is completely invalid. Like you're not supposed to do anything. You should just set it to null. That's the easy way to accidentally stop yourself from using it. Why is this dangerous? Again, if we go back to the chunk diagram. So let's say I had a free chunk, right? I had an allocated chunk and I freed it. So this is now what it looks like. You will notice that the forward and back pointers and then like some other metadata and also previous size, in fact, at the end, are in the user data of this chunk. The malloc is using the user data to store all of this metadata. If I now continue to use this chunk, I can corrupt all of this stuff, right? And in particular, if I corrupt the forward and back pointers, like that usually is a quick exploit. So, and a concrete kind of example of this is Tcache
Yeah.
poisoning.
Also, I just wanted to mention one more thing. With that use after free is we talked about like, yeah, you can corrupt those pointers, like you can like basically with Tcache poisoning, corrupting those pointers ends up resulting in arbitrary, right? But some of these also, I think we might have talked about, I don't know if we
did.
actually said, some of these pointers actually point to libc. So if you have, because basically the like, I guess head or tail or however you think of it of the linked list is actually in libc because it's libc malloc. And so if you can even if the use after free even just gives you ability to read a free chunk, you can like user data or previously user data of a free chunk, you can potentially read libc pointers and then get a libc leak from there. So
Or
there's
leak the heap.
yeah, or leak the heap. There's like plenty of things that you can get just from a use after free.
Yeah, I mean, once you get one of these memory errors, it's usually like there's a lot of things you can do. I mean, there's also actually even if I mean there's kind of another angle to a use after free, which is somebody allocates a chunk, frees it, somebody else allocates a chunk and gets the same chunk, and then person A keeps using this chunk. Now this chunk is not free anymore, but they are now able to corrupt the data of the other object that was allocated. Let's say this other object throws a function pointer, like that's going to be pretty bad, right? So even if you're not corrupting heap metadata, you can still corrupt data. I mean,
Yeah, that idea is actually what happens in the first three heap
right.
challenges.
And I mean, the kind of idea is once you free a chunk, that pointer is not to be used. Like any use of that pointer is extremely dangerous. Okay, so concrete attack is Tcache poisoning. Quick, I guess, recap. You have a top chunk, you allocated 2 chunks, and now you're going to free these 2 chunks so that they end up in this free list. What we will now do is we will use a use after free to corrupt B's metadata, and we will specifically make B's forward pointer point to a stack address. Let's say we know where the stack is. malloc is again extremely stupid. It does not check that the chunk that it's returning is actually in the heap. It will happily return a chunk to you on the stack in libc, like wherever you want. If you now allocate a chunk, you will get B, which I guess depends. You get B, right? Takes
Yeah, it'll take
Yeah. Okay, so you'll get B. And now the Tcache is pointing to the stack. So if you allocate another chunk, you will now get a stack address. And that's what gives you a write to the stack. And I guess A is now gone. It's memory leaked. There's nothing pointing to it. Yeah. This is obviously bad. This is a defense against this attack. It's a total hack. It's like some kind of pointer integrity mechanism. It takes every pointer and it XORs it with like a heap address, and then it unXORs it when it uses the pointer. So like it makes your job slightly harder because you have to also have a heap leak now to break this. But like this is not really a good defense. Because it's just a like band-aid. Like it's not, there's no like it's not a principled defense. I mean, it's not solving the actual problem. It's just trying to make the attacker's job slightly harder. And I mean, you can do like any number of things. You can like override some of the bytes, and then now you get some kind of relative address. It's not good, basically. Okay, double free is another vulnerability. It's the same kind of flavor, right? Once you free a chunk, that pointer is invalid. You should not do anything with that pointer. And that includes trying to free it. If you free it, again, malloc is pretty stupid. In most cases, it will let you do that. The only thing it checks is if you are like freeing the same thing twice. So like if its free list has the same chunk, repeat that twice, it will realize. But like even if you put one chunk in the middle, like usually you can fool it. For Tcache, it's slightly better because it's a bounded number of chunks in every bit. But why is this a problem?
Can anyone,
Yeah.
anyone have any ideas of
So-
what could go wrong here?
So I guess here's kind of the setup, right? I have a chunk A, I free A, then I free some other chunk B so that I fool malloc, and then I free A again. And now my free list has like ABA. How might I use this to break malloc? I will assume that we have the ability to allocate stuff. So as the attacker, you can allocate whatever you want, and then you can modify that. Any ideas? So yeah. Right. So if I allocate a chunk, I will get A because it's at the front of the list. I can now use A, but A is in fact also in the free list. So A is now both allocated and free. And if I write any data into A, I'm also simultaneously modifying the metadata as seen from malloc's point of view. And now if I make some further allocations, like again, it's the same thing. Like once the metadata is corrupted, malloc is basically, going to do whatever you want it to. Again, like I think the actual details are slightly not important because like in every glibc version, something changes and they will add like some new defense. So it's better to just
Did you redact the the image.
It's better to just like find like the glibc version that you're working with, find the defenses, and like make sure you understand at a high level what you want to do before you kind of get into the actual steps. No, okay, here it is. Yeah,
okay.
this is, I mean, this is all of malloc. Like, I mean, you know, if you think like from the point of view of the libc developer trying to secure this, like it's impossible. It is completely like you cannot make this 100% safe. Like, and in every libc version, they will like add some or the other new defense. Like maybe they have like that pointer like authentication trick. They have some safe linking stuff they will check is like my chunk's next, previous the same as my chunk, or stuff like that. But like all of those they're just hacks, right? Because let's say they check something like that. Okay, I'm also gonna corrupt the previous of the next chunk. Now, you know, I win again. Like none of this is actually solving the main problem, which is that all of these memory errors exist.
On that note, how feasible is it to fuzz, you know, the memory related?
Yeah, I think that people have done it. Yeah, people have done it. Actually, I don't remember. Let me like after this, I'll see if I can find the paper. I remember seeing a paper where they did that. I don't remember the name. And they found like real like actual bugs, like not even like they found new exploits against malloc. Okay, so our tools, if you have not heard of phone debug, it is great. It's like GDB++ for phone. There is this heap command which will display the state of the heap. So allocated chunks, free chunks, metadata, and so on. You can also kind of get some more fine-grained information like in one type of bin. And then with heap chunks like shows you this nice graphic of the heap like color codes. Yeah, this is good. This is really good. So this is a so I mean, if you haven't heard of Shellfish, they are very famous CTF team and so on, where they have put together a guide on heap exploits, and this contains like a list of POCs, basically proofs of concept of various kinds of exploits on different libc versions. And like they start off simple with like the kinds of stuff you're doing. Eventually they get into like some pretty insane stuff, like forging chunks on the stack and then like 5 pointers pointing.
Yeah, or did you know you can like totally destroy malloc with a single null byte overflow?
Yeah. I mean, again, it's like once you break memory safety, given how complicated malloc is, like it's basically over. Like, you know, there's always going to be some edge case that the libc people didn't think of. So yeah, you should look at this. This will be useful for solving the challenges, also for just like CTF challenges. You might like literally find the exploit you want on this website. There is also this page. I'm not sure if, yeah, I think it's the second one. Or no, it's the third. It's the third link here. They have kind of like a English description of like the algorithms involved in malloc. So like when you call malloc, what steps does it follow? And it's a lot easier than trying to read the source code. So if you're interested, you can look at that. Yeah, I think the second link is like the same flavor. I would recommend the third one. I think that's the one I looked at. Yeah, next meetings.
Yeah, this Thursday we'll have a LAN party, so come out to that, you know, fun time before spring break. And then yeah, no meeting this Sunday because of spring break. Reminder, after spring break, we'll be playing Dice CTF, so come for that. They'll probably have some cool heap challenges. And yeah, there's the meeting flag. Yeah.
Yeah, and then I guess the meaning of this, for some reason, like the heap people, they call every exploit like house of something. I don't know what it is.
Yeah.
Like house of, like, what is it?
Hotcake.
Yeah, house of
Yeah.
hotcake is.
Yeah, it's like so random.
I think this actually comes from like there's this magazine called Frack. Probably you might have heard of it. The original stack smashing exploit was demonstrated in a very, very famous article called Smashing the Stack for Fun and Traffic.
Yeah, yeah.
And I think a few years later, somebody else wrote something similar for heap exploits. And for some reason, they decided to name all of their ideas House of whatever. Yeah. I mean, if you're interested in like history, you can read that.
Yeah, also in how to heap, the like exploits are,
Yeah,
the
they're
names
all
are there,
House of-
yeah, house of whatever.
Yeah, I guess to do the challenges, we have a bunch of challenges. They aren't actually that bad. Like they are.
The heap challenges
straight.
are pretty good, yeah.
I think the last couple of them are maybe a little tricky, but the initial few are totally. I mean, they're not going to involve you trying to understand like some minor details of malloc implementations. They're more just general concepts, and like I don't think we give people even the like latest libc versions.
No.
They're pretty old libcs.
Yeah.
Questions?
Like any questions about malloc, because that was, you just learn malloc and then learn how to break malloc all in like 50 minutes.
How does it, you say they coalesce forward, but they don't stay, but they never store if a chunk is free or not. So how does the chunk know that the next chunk is free?
Or it'd have to go
Yeah,
2
zero.
chunks, yeah.
Yes.
It's like,
Two.
well, the reason like the reason why you need to do pre-bin use though.
No, pre-bin
That's
use
the-
is reasonable.
Yeah,
Because then you want to go back. Well, actually, it's not reasonable.
well,
Because you could just store whether it's free or not. You could store
Yeah.
pre size and you just
well,
go up
look,
to-
look, so the reason why though is because pre size here
Yeah.
is not a constant metadata field. It's
Sure.
also only in free chunks. Or like,
Sure.
so
Yeah. Okay.
so if you just store the current
Yeah.
bit is free, right? How do you know whether the previous chunk is free? You need to actually go to the previous chunk's metadata. The only way to do that is use prev size. What if an attacker forged the prev size data for an actually in use chunk to jump to
I mean,
forged
not even an
metadata?
attacker, right? Just regular user might corrupt it.
But true, yeah, even the regular user might corrupt it. Yeah, so like that was actually my UAUCTF challenge, by the way. But like, yeah, so if you only have the prev size fields in a free chunk, which is a memory usage optimization, then you can't just use a prev, you just can't use a current chunk as free bit. Because then you're working. Yeah. So you have to do the little bit gross, like
I mean, this
go
is-
2
yeah.
chunks and then like, yeah.
Like they're trying to do this to save memory.
Yeah, yeah.
Like 4 bytes per chunk, and it leads to all of this complexity.
Yeah.
Like if I were implementing this, I would just like do it with like a good design.
Well, I mean, like saving memory is pretty important, I think. But yeah.
No. Yeah, I was thinking that because I'm in 341, I wrote now,
Yeah,
and I just use the 3 bit and I go 3 3.
because we do like boundary
Right.
tags, right? This is like a boundary tag, but it's like it's only in free chunks, right? And because the prev size is actually technically it belongs to the previous chunk, not the current chunk.
Yeah.
But they don't put it in allocated chunks because they overlap it with the memory.
Right. So I guess if they found a different way to like organize, like, because they have technically there's 3 bits that they can use since size is aligned to 16 bytes. So like, if they found a way, I don't know, like, I guess 2 of those other bits are used for whether the chunk is M mapped and like that what arena it's in. But like one of those I didn't need to use anymore for whatever reason, then they could put like a current is in use and then like make things a bit easier. But
Another idea, which is I think what the kernel does, is they don't even put their metadata in the chunks. They put their metadata somewhere completely different. So their chunks are just user data.
What do you do?
Well, you like store all of your, your malloc state somewhere else. Like you might store, your free list would just be like pointers, right? And then like maybe struct, like just the metadata. Because like the allocator does not actually need to know about the allocated chunks, right? It only needs to know about the free chunks. Yeah.
anything else? All right. Thanks for coming,
Yeah,
everyone.
totally
Oh.
right. This is something I don't know, I've just heard of it. Do you know what heap spreading is? Can you explain?
Yes, actually. So
Like, it's
heap
like heap
spraying,
offset.
right? So heap spraying is a ASLR bypass technique. It's kind of like knob sled on steroids. So the idea is as follows. Let's say I gain a maybe a arbitrary read, right? Or I guess even more easy. I get a shellcode exploit. Like I get a code execution. I can jump to a arbitrary address and execute code starting from there. But let's say I don't know my stack address, so I can actually do a stack shellcode exploit. I don't even know my heap address, let's say, but I can at least write things to the heap. I can allocate objects. So the idea for heap spray is that I will allocate a very large number of objects on the heap, basically fill up as much of the program's memory as I can. Inside each object, I will put, let's say, an offset and shellcode. And then I will just jump to some arbitrary.
Right, in any of them, right?
Right,
Yeah.
it just increases the surface that you can, like it
Okay.
increases the size of the target, basically.
Yeah, I was asking this when you run like a terminal blue and Metasploit, it'll be like, hey, we're gonna try to create like 2,400 corrupted eggs, and you have a 33% chance of hitting per fire.
Yeah.
And we're gonna run it 12 times. It's
Right.
like, I have no idea why you would have a probabilistic exploit, that's what I was asking. Does that make
Right.
sense?
I mean, because ASLR is a probabilistic defense, right?
Yeah.
So it's not a real defense. It's a hack. It can be like it's not solving the real problem. The real problem is memory corruption.
I mean, this is like, again, getting too philosophical, but isn't the real problem just inherent in any like bond-knowing architecture, where you have your data and your code all bundled up?
Well, yeah, but I mean, you even if you know, like the example here was code execution, but like let's say, you make the heap non-executable, which is what usually is the case. Let's say I have like, I mean, common example, right? That there's like kernel objects that might contain some useful secrets, let's say. Let's say I have the ability to allocate these objects, and I want to leak one of these secrets. What I can do is I can just allocate a whole bunch of these objects, and it's reasonable, like threat model reasonable to assume that the attacker can allocate these objects because, like, let's say if they open a bunch of files or something, they're going to end up allocating objects. And then I just try to read some arbitrary address,
I
right?
see.
I have a much better chance of succeeding, right? I mean, it's just a strategy where you basically just increase the size of the target. And then you just shoot randomly, and you're more likely to hit the target.
Okay, cool.
Yeah. Browsers also, this is a common,
Yeah, it's
Trick.
for V8 stuff.
because JavaScript can allocate objects also, right? Like if I write JavaScript to create a bunch of arrays, it's gonna allocate heap objects.
So you think of it as random browser is common.
At first, I thought you said it's an IOC, but yeah, that makes sense, actually.
I mean, it's basically an ASLR bypass.
Okay.
It's the same as like, like a knob select kind of does the same trick, right? Like you increase the range of addresses that you can jump to.
Yeah, now so that you get like, I think, a lot more likely, like these brains be really unlikely.
It depends on circumstances. But you can, like, it's just like if I allocate 1 million objects, like with some very rough math, my chances are now 1 million times better, right, on a random jump. And maybe like my jump is not even random. Like I know like my heap is certainly not going to be at like 0x000000, right? I have some rough idea of where it is. Like I think actually user space ASLR only randomizes 12 bits of the heap,
Oh, okay.
not the entire address.
Or yeah, it'll always start at like 0x555
Right.
5 or 556 or something.
And it's aligned on like page aligned or something at the end. So yeah, it's actually pretty effective. We should make a challenge, heap spray challenge.
Right. Yeah.
You should write a like really shitty AI generated code swap browser, right? Something just riddled with problems where it like just Lua for something really cursed,
Yeah.
but like do it really badly. and then go from there.
Well, JIT is another big problem, right? Because JIT necessarily breaks DP. Like, when you
Yeah,
JIT
yeah.
code, like, you
You're
need,
giving them code case, basically, like, you have a bunch of caves, you just like, hey, jump here, right, you can arbitrary right to jump and you win.
sure. Yeah, so do the challenges, good challenges, no heap sprays in the challenges.
No heaps race. Sorry to disappoint.
Yeah, but you can allocate objects, right, in some of them.
Yeah, they say like keep no challenge.
Yeah.
All right, thanks for coming, everyone.